All right, so hypothesis test with proportions. So we're still going to be dealing with percents today. So showing you this is not going to totally screw you up before your quiz on Wednesday, because a lot of the same steps, especially at the beginning, are exactly the same. So it's kind of a review in a way of what's going to be on your quiz Wednesday, especially with the assumptions, which I know is kind of confusing the way some people, looking at those going, what am I doing those assumptions for? So we'll go through them again in the hypothesis test. With the hypothesis, so excuse me, what you have to kind of, sorry, my voice ain't working yet. You have to kind of look at is what you're doing with the hypothesis test is you are proving, sort of in a way, whether or not you think somebody's actual guess or evidence is enough to prove that something about the population is or is not true. All right, so that's what the hypothesis test is. So we're almost looking at this from the other direction. Whereas a confidence interval says, hey, I'm like 90-something% confident that it's between here and here. The hypothesis test says, hey, I got this answer. Does that really fit with what you were originally saying? Why and why not? So we're looking at it from the other direction where we actually got our result. And now we want to know if what we got makes sense. So you're going to have different types of hypotheses to look at. Your original one will be equals to, and then you'll make a guess or a test on whether it's actually less than, more than, or not equal to whatever one the population is giving us. We test this by calculating the probability we would get our sample or something more extreme than the sample if the population proportion really was equal to what the claim is. All right, the one that the claim is from the population, that one's called the null hypothesis. You're going to see that phrase quite a bit when we're doing these hypotheses. Yeah, the null hypothesis, the original one, it's the one that's been unaltered. It's the one that comes from the population we assume. Then we're going to say that we would reject the null hypothesis when we get to that point, and then we'll accept the alternative one. So we're going to have two of them to look at, and we're going to be basically testing if the one that was given to us as the population one makes sense or not. All right. Again, a lot of this stuff is already in your notes. So you don't have to write this down. I'm just kind of explaining it as we're going through there. If that probability of getting what you got for your sample is very small, what that most likely means is what Skylar was just saying, that your null hypothesis is false. So we're going to reject it. And then we would say that there's enough evidence to support the alternative one, which means it's less than that, more than that, or just different from that. If the probability is not very small, that means this random sample that I got kind of makes sense, then there's not enough evidence to change anything. We do not reject what we call the null hypothesis or the original one. We didn't prove that it's true. There's just not enough evidence to prove that it's false. All right, so welcome to the world of statistics where we don't actually know the exact answer. We just know that it's not this. So we'll fail to reject the original hypothesis. We'll go with it until we get enough evidence to say otherwise. And that means that everything stays like it is. You don't have to change anything. So as we're doing this, remember what you're rejecting or failing to reject is the original null hypothesis. You're not actually rejecting or failing to reject the alternative. The alternative is just what takes place of the null if the original one is bad. So what are going to be all my steps for all this? So just like before, we're going to have assumptions. Before that, we need to state what our actual hypothesis is. This comes from the word problem. And then again, this is why we're doing this before your actual quiz on Wednesday over confidence intervals. The same assumptions are there. A lot of the same calculations are there, so it's a good review. We're going to use the actual population percentage instead of p hat in our equations this time when we do our assumptions. And then our calculations, we'll have the formula. You guys can see it in your notes there. You're going to find the z-score, or what they call the test statistic, if you want to. And I'm going to show you guys how to do this here in a minute. We're going to sketch a picture of the graph so you guys can kind of see which direction things are going in, so you can make smart decisions based on what is being shaded underneath the normal curve. You're going to calculate the p-value. So we got like all sorts of little letter p's going on here. So let's go ahead and separate them real quick. This one is the percentage that the official population claims to be true. This one is what our sample got us, and this one is the chance that we get this sample. So there's going to be three of them there, so you're going to have to watch all your little labels. It's going to get confusing pretty quick. And then your alpha is going to be at the level which you decide to reject or not reject your hypothesis. So if it's above it, you're good. If it's below it, you're bad. Typically, this alpha we'll see is at 0.05. So at 5%, that's kind of our red flag, too low level. And then because this is a scientific experiment, basically, we still have to write a conclusion. And then your sentence is still provided to you, so you don't have to think this up. I remember I like it as systematic as possible as we go through these things. So a lot of the steps and setup here, again, very similar to the confidence interval. So this is kind of a review, except we're just looking at it from the other direction. So we're actually, doing something that people would do in real life and make money at this stuff, because we would test what we got versus what they claimed and see if there's enough there to make a difference. So here's how you would write your hypotheses for your proportions. You're going to write two of them. Your HO, all right, looks like your, your HO is your original null hypothesis. This is your P that comes from the actual equation or word problem. Your alternative is the one that you're going to accept if this one is proven to be false. So it'll have a greater than, a less than, or a not equals to same number. All right, so I had a student last year that used to make me laugh. He's like, Mr. G, help me with my ho-has. Okay, you'll see it over and over again. HO is the null hypothesis. HA is your alternative hypothesis. We're trying to prove this one. If it's false, then we'll go with this one. If this one we can't find enough evidence to say it's false, we keep with this one. Okay, so that's the whole point of this test. We have to define what our percentage or letter P is in the context of the problem each time we do this. So we'll have to write out where P is the true population proportion of, and whatever we're looking at. All right, so this will be your first step. This is in addition to everything else we've already been doing. So you're like, yay, Mr. G, more work. Yes, these problems have now gotten one step bigger. All right, again, this symbol here can be different. You'll know which one to do based on the wording of the equation. So am I testing that it's more than, less than, or not equal to? Formula for your test statistics. So this will look familiar from your confidence intervals. This will give you the Z-score in which you will actually run your test on. So to find your Z-score, you're going to take your samples percentage minus your population's percentage. So notice there's a difference there. The little hat on this one means this is from my sample. This one means it's from a population. And then this right here looks familiar. We've already used this part before. It's P times 1 minus P over the sample size. Now, for those of you guys that are really statistical savvy, like you're just seeing things like a savant, and this class has been too easy for you and it's not been a challenge yet. This formula looks very familiar to something that you've seen before, just with different letters. We had an old formula that we did back in like September that said Z is equal to X minus the average over the standard deviation, right? Remember this formula? So all of this right here, this one right here, this is your X value. It's just written in a different format now because we're doing percentages. This comes from your population as an average. So there's your little mu symbol. And all of this down here replaces your standard deviation. So all we're doing is plugging all this stuff in. We get a Z-score. And so that means somewhere on my normal curve is going to be where my little line's at. So again, this is only for people that have been like really seeing this class, like, you're seeing patterns, you're starting to see how things are all coming together. We're doing the same thing here. We're just replacing the letters with what's relevant to our current situation, but it's the exact same process. How far away from my average or how far away from my percentage is my sample? Is it too far? We got a problem. Is it close enough? Okay, it happened by random chance, we're good. So that's really this whole thing. If you can kind of look at this hypothesis test as really just a super fancy way to see how far away your sample is from what it should be, that's it. We just got to go through all the steps to statistically prove it with significance. That's all we're doing. All right, so this is in your notes. Again, pay attention. This one is P hat. The rest of them come from the actual population that it gives you in the word problem. So don't accidentally use this one down here or you're going to have oopsies. All right, once you get your Z-score, all right, from the formula that I just showed you, once you get your Z equals, calculate and get a little number, choose like 1.6 something or negative, 2.3 or whatever. It's somewhere in that type of number. You can now plug that into your calculator using the second VARS option 2 to figure out the percentage of the graph that's shaded in that little region that you just figured out. So this p-value will calculate the likelihood it was that Claire got that sample if she's testing something, or Maddie got that sample she was testing something. All right, so the p-value is not your percentage of like the actual population. It's the chance that the sample you got exists. If it's really small, the percentage of this p-value is really small, usually less than 5%. There's a red flag there. You shouldn't have gotten that sample by random chance alone. Something's wrong with the original hypothesis, therefore we reject it. And we don't know what the real answer is, but we know it's more than, less than, or not equal to what we originally had. So this p-value is going to be important. So again, we're going to use normal CDF in the calculator. That's second vars, option number 2. All right, your average and standard deviation always stays 0 and 1, just like we've been doing with all this stuff. And then you just have to decide what your upper limit is, lower limit is, and you're good to go. All right, calculate that p-value for you in the calculator. It's going to give you that percentage. Then you're able to draw a pixel, label your z-score, shade your region, whatever you need to do. This is called a one-tailed test for these. All right, if you're just testing as more or less than that. If for some reason you're testing that it's different, meaning it could be upper or lower, then you would have a two-tailed test, right? Where you have area on both sides of the graph, and you just have to do one of them and multiply it by 2. That's the easiest way to do it, because they're going to be symmetrical. Everything about these normal graphs, remember, is symmetrical. All right, so we're going to do example of one of each of these so you guys will see it. All right, so first off, let's test that you guys can do this stuff in the calculator by, define your p-value first. Then we'll go ahead and actually do a full-on beginning to end, step-by-step analysis of a hypothesis test. So if you need a calculator, grab one. I just want you guys to practice typing things into the calculator using second vars number 2. Let me make the screen a double. All right, there we go. So I want to do I got this hypothesis that P is equal to 0.2%. If not, then I'm going to assume the alternative that it's less than 2% or 20%, sorry. And so I did my calculations in my little formula. So I went through and I did all of this already. And I plugged in my P hat, my P times 1 minus Pn, and I came out with this negative 1.2. So now I'm ready to do my p-value. What's the chance that my sample is what it is? So we go to second, we go to vars, we go to normal CDF. Which direction is this inequality facing? It's saying less than. So it's faced, for you guys on Zoom, it's this way. It's facing to the left. So that means negative 1E99, because I don't have a limit on the left side of my graph there. And then this negative number is my upper limit. So negative 1.2. Leave these at 0 and 1. Okay, so if I'm drawing a little picture of what my graph looks like here, this is our normal graph that we've come to know and love, and we're going to keep using it. Right down the middle is always 0. 0 z-score, 0 standard deviations from the mean. So negative 1.2 is somewhere back here. All right, this is my z-score. So it's basically telling me I'm 1.2 standard deviations below the average. And I want to measure basically the percentage or area of this part of the graph. So how likely or unlikely is it for me to be in this region? So basically, what's my percentage there? So when I press enter, that's what it's going to tell me. So that's why we're going to the left on this one, because the area stops at the 1.2 negative and goes backwards. So it's telling me that the shaded area or region of this part of the graph is 11.51%. All right, well, that percentage is not unusual. I know for us, it seems like only 11%. That's not really very likely. But as far as random chance goes, it's likely enough that on this particular one, we would fail to reject our original hypothesis. So we would just keep it at 20%. There's not enough statistical evidence there to say, my number is really weird. It's on the lower end of what we would expect, but it still works. It's within that confidence interval that we did last class. We're just looking at it from the other side now. Oh yeah, we got a drill coming up here in a second. I'll explain it soon. All right, so now let's try one that is to the right. Now I'm going to test to see what's the likelihood that my sample being greater than 20% exists. So again, plug everything into my formula. My z-score is this. If I'm looking at my picture, again, here's my little normal curve. 0 is down the middle. All right, 1.6 is somewhere over here. So what's the likelihood that I get something like that or bigger? Because my inequality this time is facing or pointing to the greater than sign. So second, vars, option 2. So my lower limit now becomes the 1.6247. My upper limit, well, I can keep going. So 1E99. Again, leaving these at 0 and 1. Don't change those. No need to. We're just looking at a good old standard normal curve. What's the percentage of the area there? Ooh, it's close. It's just a little bit bigger than my usual 5%. So 0.0521. All right, so this is probably the most important calculation you do on this hypothesis test. Can I determine the likelihood that my sample exists at everything being the current setting that it is, and make a decision based on whatever my alpha is, or my, what they call, significance level. All right, anybody getting stuck on the calculator stuff so far? Are we okay with this? All right, last one to look at is, well, what if, Mr. G, I decide that I just want to test if it's different. I don't really know if it's greater than or less than, because sometimes we don't. So I'm just going to test that it's not equal to 20%. On this one, this is what we call a two-tailed test. So we have, again, our graph with our average and standard deviation at 0 in the middle. All right, well, negative 2.05 is back here somewhere. But since we're doing a two-tailed test to determine whether or not it's just different than 20%, we also have a positive 2.05 z-score on this side. So we're testing this area and we're testing this area. So with the not equal sign, you're doing two spaces. They're both symmetrical. So once you figure out the left side or the right side, whatever it is that you want to figure out, then you just multiply it by 2. So in this case, I would do second vars, option 2. All right, I'm going to test the lower one because it's already negative, so it's easier to do that. So negative 1 E99. And then my upper one is just going to be the negative 2.05. That's as high as I want to go on my graph here, and paste it this way. So I'd get this number, and I can just multiply this by 2 because both of these little sections over here are going to be the same. I don't have to test it the other way. If not, what you'll do is you'll get this same number twice, and you can just add them together. All right, so for those of you guys that are like, well, wait, are you sure, Mr. G? Yeah, if I accidentally did it the other way, positive 2.05 and 1E99 this way, I'm going to get the same answer I got before, 0.021. So again, adding those together or multiplying one of them by 2 gives me the same result. So I have a larger area where things could shift, and I can decide whether or not it's likely that I get something that's different. So again, if you think of this as a reverse confidence interval, you're now testing the remote 5% or 10% left over that you didn't want to have your original confidence interval. So your confidence interval was like, I'm 90% sure it's between this and this. Okay, well, we got something out here. Is it inside of it, or is it outside of it? And so that 5 or 10% that we're testing at is the part left over in the graph that we didn't want it to be in the first place. If it's out there, then then your original result is wrong. If it's not, if it's inside, then you're good. All right, so if you think of it like that, that might help too. Just depends on how your brain's working with all this stuff. There's a lot going on all at once. But again, are we okay with typing this stuff into the calculator? All right. So at the very end, you've got your p-value now. You can make your determination if it's less or greater than whatever your alpha is. Again, we're going to learn that the default for this is 5%, but it can change if I want to be more or less picky about my test. If your p-value is very small or smaller than this, then you're going to reject your original hypothesis because there's now evidence to show that your original hypothesis is wrong. And so you would accept the alternate one, that it's more than what you got or less than what you got or different than what you got. If you run all your tests and your p-value comes out to be greater, again, typically more than 0.05, but it can change, then you would say there's not enough evidence to show that my sample is weird, basically. And so our original hypothesis will not be rejected. I failed to reject it. There's not enough evidence to change it. And so you just go with what it was. Again, you don't prove anything is true. You just prove that something is or isn't false. All right, unless we state otherwise in the problem, and it's on your notes, you don't have to write this down. Assume that that little alpha symbol, your significance level, is at 5%. Okay, so unless somebody comes by in the problem and says, we're going to do it at 10% this time, or we're going to do it at 20% or whatever, assume that it's 5%. This little alpha symbol is also called the significance level in certain texts. So depending on which homework assignment and stuff you're looking at, you might see it written as that. All right, so those are all of the steps. We're going to go through one of these whole things together from beginning to end. I'm going to let you guys see how this works, and then we'll let you try one on your lonesome. All right, so here's our example. Let me get my piece of paper ready. A company is willing to renew its advertising contract with a local radio station if the station can prove that more than 20% of the residents of the city have heard the ad and recognized the company's product. The radio station conducts a random sample of 400 people and finds 90 have heard the ad and recognize the product. Is this sufficient evidence for the company to renew its contract with the radio station? So basically, this is a real life type of scenario. An advertising agency is like, hey, we got this product. We've been advertising with you. We appreciate it, but we want to renew our contract and spend lots more millions on you so you can sit around and talk about whatever you talk about. Radio station's like, awesome. The only caveat is, or the only condition is, can you prove to us that enough people are listening to our ad to make it make sense for me to spend money here? So the radio station's like, okay, let me go do a survey. We'll come back. We'll let you know. So that's what's going on here. So you work for the radio station as a statistician. All right, if you guys are into broadcast, they need statisticians all the time. So it's a very likely career path. And you're going to go prove without, too much doubt that there's actually evidence out there that people are listening to the deal. So blank piece of paper. Let's walk through this thing. Let's set it up so you guys can kind of see it. So there's 4 different things we're going to do instead of just 3. So the first thing we got to do is we got to state our hypothesis. That's step number 1. You got to know what the heck you're testing. So the original population percentage of people that are supposed to have listened to the ad, our null hypothesis, H0, is supposed to be equal to 20% or 0.2. What we need to do is verify whether or not we have a sample large enough to convince the advertisement agency to continue to advertise with us because we want it to be more than 20%. So if I look at my little section on the notes here without going too much into all my answers yet, we're looking for more than 20% to be our verification that they can continue to advertise with us. Does that make sense? So that tells me right there which way my inequality is. If it had said different from 20%, we could put not equals in there. If it had said less than 20%, we could put less than 0.2. But this one said more than. Now we have to define what the letter P is here. Somebody's going to come back later, read your report. They need to know what this little letter P represents in this particular problem. So we're going to say where P is the true population proportion of people who heard the ad. So I'm just getting this phrase from the actual word problem itself. Can you guys see that okay, or do I need to write in pen? You good? Okay. So that's it. That's our first section. Write out your hypothesis. So before you even get started, you got to know what you're looking at. All right. Next up, I need to do my assumptions. So before I start typing things into the calculator and do my calculations, I got to make sure my sample meets all the requirements in order to do this. So being a statistician is not as easy as you guys thought it was when you signed up for it back in March of last year. All right, so go through my assumptions. There's 3 of them. All right, 4 different things we test, but we're looking for 3 things. Number 1, we got to check that it is random. Because why? Well, in this case, did they take a simple random sample of whatever? Well, yes, it said a station conducts, and it's right here in my underlined section here, random sample of 400 people. So that's it. My qualification for it being random has been met, because they can't just go pick, the 400 people that they know for sure like the ad. They've got to prove that it's random. So simple random sample of 400 people. Check. So the randomness is verified. We're good. All right, these are the steps that you still have to do for your confidence interval. So this is the part that's reviewed here. All right, now we got to check that it's normal, because 2 things. That n times p, which in this case is 400, times what is my original hypothesis. This is the one we use, not p hat, but we use this one in our calculations. 0.2. It happens to be the same number, so it's okay. But you just need to make sure you know it's this one. All right, so 400 times 2 gives me 80. Is that greater than or equal to 10? Yes. All right, so remember that one. We got to have a sample large enough that it can be normal. We also have to check that the n times 1 minus p, which in this case is 400 times 0.8, all right, that gives me 320, is greater than or equal to 10. Check and check. Again, for those of you guys who like patterns in your math, there it is right there. These 2 should equal your total. All right, so we know it's random. We know it's normal. Last thing we got to check for that it's independent. I don't want to take a sample and have one of the samples affect the rest of the chances of the other samples. They all should be independent of each other. So this is independent if the population is greater than 10 times n. So we need to say that 10 times n is going to be 400. So that's equal to 4,000, which is good. All right, the population here of people listening to the radio station, I would assume is more than 4,000. Are we okay with our assumptions? This part is on your quiz Wednesday, so if you don't still get any of this, you need to be practicing or asking for help. All right, calculations. So before I do that, real quick, let me pause my recording. I got information I got to share with the in-person people here for just a second, and then we'll get back to this. So hold on. Getting my stuff here, I need to calculate two things. I need to calculate what my z-score is first, and then I'm going to take that z-score, plug it into the calculator, and see if it's really weird that I got it or if everything's okay. Then I'll make my decision to reject or fail to reject this one here. So start off by z equals, and then use your formula that's in the notes. All right, so this is the formula I'm talking about right here. So what is the p hat? Well, in this particular case, the p hat is the number of people out of 400 that said they had heard and recognized the ad here. So that's my 90 out of 400 people. That's my first number. Because I ran a survey, I came back with, hey, 90 people have heard and recognized this product. So my p hat is that 90 over 400. Minus, what is the percentage that I should get in this population? 0.2. We're okay with those numbers? So this is like my x minus u for the formula. This is what I got. This is what I should have got. Divided by, now we got to do the standard deviation, the square root of this right here is the p that you use, not this one. Don't start doing p minus 1 minus p with this number, because this is just your sample. So it's 0.2 times 0.8 over, and what's my sample size this time? 400. So now what I do is I type everything into my calculator so it matches this here. So I have a fraction. So second y equals, let me get my fraction going. What's going to go on the top part of my fraction? 90 divided by 400. You can make another fraction there if you wanted to, same thing. Minus 0.2. So that's the top part of my fraction there. Underneath, I got a square root symbol. So second x squared brings up my square root symbol. Again, I got a fraction down here, so we make it a fraction. What are my two numbers that go on the top? 0.2 and 0.8. What's my number that goes down here? 400. Questions so far? And you can do it any way you want. This is the way I type it. No problem. You guys don't turn anything on or off. Just grab your jacket. It's all you need. I'm going to lock everything up and go ahead and go out, get the fire drill out the side.